Good morning. Welcome to Krishna's classroom. We look at the convergence in LP spaces as a prelude to considering the completeness of LP spaces. So let us fix the notation. Let E be, this is all recall again. E be a subset of R, it's a measurable subset. Let script F denote the set of all measurable extended real valued functions on E, which is finite almost everywhere on F, we define a relation. The relation is that F is related to G if and only if Fx equal to Gx almost everywhere on E. Now, one can easily verify that this is an equivalence relation and therefore induces a partition on F to equivalence classes. Let bracket F designate the equivalence class containing F. So let script F denote the space of all equivalence classes for F's belonging to script F. Now, one can easily verify that F tilde is a linear space. This is the linear space structure inherited from F, which is also a linear space. And you see that there is no ambiguity about this because one can easily show that within this equivalence relation everything is well defined. So let LPE, now we try to work out LP. So let LPE, to begin with, we work for 1 less than or equal to P less than infinity. We'll consider the case L infinity later. Be defined as follows. LPE is the set of all equivalence classes bracket F in script F tilde with the property that integral over E mod F the power P is finite. So we take a subclass from F tilde. Then one can easily show that this is a subspace of F tilde. Further, we defined norm of, yet to call we have to prove it is a norm, which we have done already, bracket F, the P norm of this as integral over E mod F to the power P to the power 1 by P. Now this is well defined in the sense that if bracket F equal to bracket G, that means both F and G belong to the same class, then integral over mod F to the power P is equal to integral over E mod F mod G to the power P. Therefore, see that this is well defined. That means irrespective of what representative element you choose to represent this box or this block, that is bracket F, you always get this integral the same. Okay. So henceforth we shall designate. So it is cumbersome always to write bracket F. So we shall henceforth realize that or designate that the bracket F by simply F. With this understanding, now we can write norm of bracket FP is the same as norm of FP. That is, and you can show that that's what we have shown in the previous results by proving the holders and Minkowski inequalities and applying them, that norm P of F is a norm on LPE. Therefore, LPE is now a normed space. Okay, so we have got the structure of this particular normed space. Before we go on to look at these spaces, we will also describe what L infinity is, so that we can proceed comfortably. Okay, so let me now. So therefore, what we have obtained is this, that LPE with is a normed linear space for so that's the outcome of that, and this we know how it is defined. Now we take up L infinity. So L infinity E is again a subcollection of, that is F tilde, where F is essentially bounded on E, which means that except on a set of measure 0, the function F is bounded. Such functions we are considering. Now that's the only difference, and the rest everything goes through well. Now what you have is, we can write once again, you have this, you can define as essential supremum over E of mod F. Okay, now that we have defined earlier. Then with again our what we did earlier, so we shall, so you see that this is in fact designating valid for the same reasons that we used for the previous case, namely 1 less than or equal to p less than infinity. We have f is a norm on hence so we have defined now introduced the spaces LPE for 1 infinity with the norm defined. So what we have is, we can write this, therefore LPE normed linear space. So this is a normed linear space. Now we are essentially interested in looking at this normed linear space. Now in every normed linear space, the norm induces a metric. So let X we'll write down the general. Then dxy defined as defines a metric on hence X D is a metric space. Therefore, LP is a metric space with the metric induced by the norm. So this is what you have. LPE is now a metric space with the metric induced by the norm. So LPE metric space. defined by so our problem now is the completeness of this matrix space. So we have now the tool for asking the or posing the completeness problem. So the question that you have at this stage is this is the question that we are asking. Now, what do we mean by a complete space? A complete space is a normally a metric space where all Cauchy sequences converge in the space. Okay, all Cauchy sequences in the space are convergent to some element in the space itself. So we will start systematically working on this and also look at some results which are required for our purpose. And instead of working on LP, DP, we will work on general space XT. Or wherever things stand on general space, we will just write. Okay. So that's our strategy. So we'll now introduce what are called convergence. So definition. A sequence when in non-linear space X with the norm is said to converge F belonging to X provided the condition now limit n tending to infinity of equal to 0 equal to 0. That is given epsilon positive, there exists n epsilon such that norm of Now this is the definition of convergence. So we can talk about convergence in every metric space, therefore in every normed linear space. We'll look at some small examples, and you see that now if x equal to r, infinity. Now we'll take case 2. CAB, all continuous functions on the compact interval, continuous functions on compact interval contain graph. Let maximum of mod ft. Now the maximum exists because you are considering a compact interval and you are considering only continuous functions. Therefore, the maximum exists. Which exists? Compact and f continuous. Therefore, what does this convergence mean? In this case, Fn converges to F means Fn uniformly converges to F on the interval uniformly to f on the interval, which means given epsilon, there exists an n which depends on a, of course, epsilon only, and not fn converges to f. So point-wise fn converges to, that is fnt converges to ft. So what you are saying is that fnt converges to ft. It is uniform convergence, means irrespective of t, given epsilon positive, there exists a number n which depends only on epsilon and not on t, such that the condition is satisfied. Okay, so that's it. It's Fn uniformly now in L infinity, Fn converges to f means f uniformly on the complement of a subset of E of measure that means except possibly on a set of measure 0, on the complement of that, the function, the sequence converges to f. Okay. Now what happens in LP? Infinity. With the norm of defined as one upon p. See that Fn converges to f. Means a sentence. That's the meaning of that. Okay. So that's about the convergence. Now let us, our problem is the following. If you are talking about convergence sequences, then everything is fine. But there are spaces where a convergible sequence may not converge in space. Okay. For example, you look at the metric space. See? So Cauchy sequences. We introduce now the concept of Cauchy sequences. So let us start from the following. So let us start with R with a D, where D now if you take Q is now a subset of R and QD is also a metric space which is a subspace of RD. Now you see that the structure of R assures that in RD we have every convergence sequence converging to some element of R. Now suppose we take a sequence like the following. We write En to be equal to sigma 0 to n one upon k factor. Okay. Now each En belongs to Q. What about the limit of this? Now En converges R to E, which is not an element of Q. So you have sequences in Q which converge in R but not to an element in Q itself. Okay, whereas any sequence, any convergence sequence in R has a limit in R itself, which cannot be asserted about any sequence in Q. So we have a new class of things. Now if you set this En in R, it has the convergence property. That means it gets closer and closer as n becomes larger and larger. Okay, but eventually it just goes out of the space. Even this one, another example is if you take the interval, if you take this interval 0, 1, then you can construct a sequence. Look at the sequence 1 by n. 1 by n belongs to this metric space. So interval 0, 1. This is a subset of this. But you see that limit one. That's another example. Okay. But you see that if you look at 1 by n as a sequence in R, then it converges to an element in R itself. So what you see is that essentially it is a convergible sequence, which has the property that, what is the property of the convergible sequence? The convergible sequence is something where the terms get closer and closer, or more precisely we can define it and we shall designate it by the terminology Cauchy sequences. Okay. So 1 by n is a Cauchy sequence. So also En is a Cauchy sequence, but En does not converge in Q. 1 by n, the sequence 1 by n does not converge in the interval, open interval 0, 1. Okay, these are all examples. So we will introduce a new class called Cauchy sequences, something that nearly converges, or which is something that can be convertible by possibly putting the limit into the space and join the space. Definition. This is true in any metric space. Is said to be Cauchy a Cauchy sequence it's a convertible one. That's what it means. Essential property for convergence is there, but unfortunately the limit does not exist. The space in some cases. Provided for each epsilon positive, there exists a natural number n which may depend on epsilon such that is less than epsilon for every n Now this is the definition of Cauchy sequence, which says that from some stage onwards, the difference between the two elements, the distance between the two elements can be made arbitrarily small. So given any epsilon positive, you can find a corresponding n such that for all n and m greater than this particular n, see that if the distance from Fn to Fm is less than epsilon. But that does not guarantee that the limit of this sequence exists. So remark, In general, a Cauchy sequence may not converge. To an element in this case. Now, this is a major drawback for such spaces, because when we are working on mappings on the space and chasing a sequence which is a Cauchy sequence, which has all the traits to be convergent, you may finally end up outside the space. As you have seen that in Q, see, there are sequences which are Cauchy sequences which do not converge to an element in Q. On the other hand, in R, this is one of the basic structural properties of R. In R, all Cauchy sequences are convergent. So you don't have to search for, go outside that space to look for the limits. Okay. Now we have seen other examples also. Okay. So it's clear, pretty known thing. So I don't want to spend much time. Now we will look at some results related. I was using the word convergible sequence. So now what I want to observe is that every convergent sequence is a Cauchy sequence. Okay, before that, we introduce the property called completeness. A non-linear space equally well, this statement is valid for metric spaces. X is complete provided every Cauchy sequence to an element then you say it is complete. With this criteria, you see that complete. Then you have CAB is complete. As we have observed that you use the maximum norm in CAB, see that you have the continuous sequence of continuous functions uniformly convergent to some function on this space, and that function actually inherits a property of continuity. So it will converge to an element in CAB because you are able to show that the convergence in this case is essentially uniform convergence. Every sequence which converges uniformly, every sequence of continuous functions which converges uniformly is also a continuous function. Sorry, the limit is also a continuous function. So also one can prove that L infinity is complete. And we shall prove LPE is complete. But you see that like QD, you see that if you take the set of all polynomials on the interval, on the closed bounded interval AB, and then with the what is called maximum norm, it's not a complete space. There are a lot of examples that you can give where the spaces which are complete and spaces which are not. So completeness is a property of the space, okay, and which is something very useful. Once the space is a complete space, you are assured that all Cauchy sequences are convergent, and therefore you see you are more comfortable working in those spaces. Now let me prove some results related to this. Essentially, there are two results that we are going to prove. One, of course, that every convergent sequence is a Cauchy sequence. Here. Be a non-linear space. Then every convergent sequence in Cauchy sequence. Now the converse is not true, as we have seen already. If you look at the sequence En that we have considered, En is a Cauchy sequence that you can prove, but it does not converge in Q. Okay, so it need not be. So in Q, the sequence En is a Cauchy sequence, but it does not converge to an element in Q, whereas it converges in. Okay. So that we shall make a mention of it. Now, a more important and useful part is this. The converse. Converse is not true, except in some specific cases. Further, a Cauchy sequence in X is convergent if it has a convergence subsequence. So once a Cauchy sequence has a convergent subsequence, then the original Cauchy sequence is convergent to the same limit as to which the subsequence converges. Okay. So let us prove this. Now this is the main result that we want to prove. Okay. We first prove this. Then we can use the triangular inequality for norm. The triangle inequality norm, we have norm of Fm. For every element. It's very simple. Argue that it's a Cauchy sequence. So what do we do? So we'll write the argument. So given epsilon positive, such that right, corresponding to epsilon by 2, there is an n such that this is 2. Now choose epsilon. Then we have that is so all convergent sequences are Cauchy sequences, but we have already seen there are Cauchy sequences which are not convergent. So that we have already seen. Now we go to the next part. Suppose spaces in which convergent sequences not convergent sequence, Cauchy sequences need not be convergent. For example, if you take Q with the usual metric or usual norm, okay, there are Cauchy sequences. There are sequences of rational numbers which eventually do not converge to a rational number. Okay. Or convergent to a rational number. We have seen En. En is a sequence of rational numbers, which is a Cauchy sequence, but it converges to, it does not converge to a rational number. It in fact converges to the most celebrated number. Okay, so that's important. Okay, so the converse does not. Now we go to the second part. A Cauchy sequence in X is convergent if it has a convergent subsequence. So what we want to prove is this, that suppose Fn is a sequence which is a Cauchy sequence but has a convergent subsequence. And we want to assert that Fn converges to some element in the space itself. Okay. So let subsequence of Fn which converges to And what we claim is so that the existence of a subsequence which converges essentially guarantees that the sequence itself is a convergent sequence. So let epsilon positive given. Since is a Cauchy sequence, we may choose n such that greater than n. Now what we look at is this subsequence Fn. Now, since Fnk x k such that nk is greater than n, and that is possible. Okay. By the triangle inequality, we have to test the convergence of Fn to F. So how do we do that? We estimate that. Norm of we add and subtract Fn k to it and then use triangle inequality. Now you see that this is less than epsilon by 2 for every greater than or equal to. So this is less than epsilon 2. So this part is less than epsilon 2. And this part is Fn minus Fnk. If n is greater than n, then you see that, and nk is greater than n, then this again is less than epsilon by 2. Which implies because we have earlier assumed that this is a Cauchy sequence of both nk and n greater than capital N, means that this part is less than epsilon by 2 and this part is less than epsilon by 2 by our choice of n. Okay. So the sequence, the original sequence itself will be converging to F. But this is a very useful result, because instead of, when you want to show that a sequence converges to a given sequence converges, what we need to show is that two things. One, it is a Cauchy sequence. Secondly, if you can pick a subsequence of that which converges, then you are done. So the original sequence itself will be a convergent subsequence. In fact, this is the path we are going to follow to prove the convergence of LP spaces. Okay, because what we would require to prove is the following. In LP, we will have to take any Cauchy sequence and converge that and show that it converges to an element in LP. So it is a Cauchy sequence is given. Now, with certain attributes, we choose a subsequence, or we show that on the property of the space that we are considering, there exists a subsequence with a special property which converges in the space. Okay, so that the original sequence itself is convergent. And this would be the strategy that we adopt to prove that LP is complete. And this is one of the major things, okay, which substantiates or which rewards the entire work that we have been doing all along by introducing the so-called Lebesgue measure and then the concept of integration, or completely reworking concept of integration, etc. So the greatest achievement would that LP is complete for all P lying between 1 and 2. It is not for just any special P that is true, but for every P, the space is a complete normal linear space, or what you call these days called Banach space. Okay, thank you very much, and that's the place I think we can stop, and we will take up the story.